When paleontologist Mike Voorhies discovered a rich fossil bed buried under 10 feet of ash, he quickly realized it was the scene of a sudden catastrophe, of a type the scientist had never imagined. Only a volcano could produce that much ash, but finding the source of the eruption would reveal an uncomfortable truth. There was an ancient supervolcano somewhere under the western United States, one that 10 million years ago erupted with truly earth-shattering force. But as more scientists began to examine the data, they realized they weren't looking for an ancient supervolcano. They were looking for an active one, and its time has come. In the summer of 1971, paleontologist Mike Voorhies was exploring some grassy farmland in eastern Nebraska. Passing through a small ravine, he spotted a curious glint in the ground above and clambered up to take a look. What he had seen was the perfectly preserved skull of a young rhinoceros, which had been exposed by recent heavy rains. And beyond the skull, it turned out, was one of the most extraordinary fossil beds ever discovered in North America. A dried-up waterhole that had served as a mass grave for scores of animals. Voorhies discovered the full, well-preserved skeletons of rhinos, zebra-like horses, saber-toothed deer, camels, and turtles. All had died from some mysterious cataclysm 10 to 12 million years ago, in a time known to geology as the Miocene. When the initial rush of excitement had passed, Voorhies and his team were left pondering a mystery. How had the fossil bed come to exist in the first place? The ancient animals were so well preserved because they had been found buried under volcanic ash. In places, it was 10 feet or 3 meters deep. Today, the site is called the Ashfall fossil beds. Ashfall is always deepest near the source of the eruption. The further you travel from a volcanic eruption, the less ash you'll encounter. The depth of the ash at the fossil beds suggested they must be no more than a few miles from a volcano. The puzzle of it was that there were not, and never have been, any volcanoes in Nebraska. Voorhies sent samples of the ash to colleagues all over the western United States, asking if there was anything about it they recognized. Halfway across the country, geologist Bill Bonnickson was given a sample, and he did recognize it. Bonnickson had been studying a massive volcanic eruption that had taken place 10 to 12 million years ago in an area called the Bruno-Jarbidge Eruptive Center. The ash from his eruption matched the sample Mike Voorhies had supplied. The volcanic eruption that had killed the animals in the Nebraska Ashfall and buried them under a layer of ash 10 feet deep had happened more than 1,000 miles or 1,600 kilometers away in Idaho. It was a volcanic explosion on a scale previously unimagined. A supervolcano, an eruption of catastrophic proportions, apocalyptic in scale. In his book, 6 Easy Pieces, renowned physicist Richard Feynman wrote, "Strange as it may seem, we understand the distribution of matter in the interior of the Sun far better than we understand the interior of the Earth. We know amazingly little about what happens beneath our feet." When in 1880, geologist and engineer John Milne created the world's first modern seismograph, scientists got their first glimpse into the inner workings of the Earth. In 1909, pioneering Croatian seismologist Andrija Mohorovic used seismic data to establish that the Earth had several distinct layers. He also identified the boundary between the Earth's upper layers, the crust and the mantle. It's called the Mohorovic discontinuity. In 1936, Danish seismologist Inge Lehmann, analyzing seismic P-wave data, suggested that the Earth must have a solid inner core. Today, scientists generally agree that the world beneath us is composed of 4 layers: a rocky outer crust, a mantle of hot viscous rock, a liquid outer core, and a solid inner core. We know that the surface is dominated by silicate minerals such as quartz, which are relatively light and not heavy enough to account for the planet's overall density. Therefore, there must be heavier stuff inside. We know that to generate our magnetic field, somewhere in the interior, there must be a concentrated belt of metallic elements in a liquid state. That much is universally agreed on. Almost everything beyond that, what the layers are composed of, how they interact, and what causes them to behave in the way they do, is a matter of at least some uncertainty. Even the one part that we're most familiar with, the crust, is still the subject of scientific debate. In the late 1700s, the father of modern geology, James Hutton, observed how his own farmland was subjected to the slow process of erosion. Rocks were eroded away, creating soil, which was then washed into streams and rivers and deposited elsewhere. He realized that if such a process were carried to its natural conclusion, over millions of years, the earth should be worn quite smooth. However, he was surrounded by hills, mountains, and valleys. Hutton also knew that marine fossils had been found on mountaintops. The thinking at the time was that they got there during the Great Biblical Flood. Hutton wasn't so sure. He believed that there were unknown geological processes at work. It was a mystery that would take 200 years to solve. In 1908, around the same time Andrea Mohorovic was using seismic data to learn more about the interior of the planet, an amateur geologist named Frank Bursley Taylor proposed something that to many seemed outlandish. He was struck by the similarity of the facing coastlines of Africa and South America, and he deduced that the continents must be moving across the surface of the Earth, and it was the collision of continents that thrust up the world's mountain chains. He failed, however, to produce much in the way of evidence, and his American colleagues ignored his crackpot theory. In Germany, however, a meteorologist named Alfred Wegener had been working on a similar theory. Wegener also reasoned that at some point in the distant past, many of the continents fit together in a grand geological puzzle. He also investigated the many plant and fossil anomalies that did not fit comfortably into our understanding of the Earth's history. There was simply no way to account for plant and animal fossils that repeatedly turned up on opposite sides of oceans that were clearly too wide to traverse. He presented a formal and well-supported introduction to his theory to the Geological Society of Germany in January of 1912. He called it continental drift. Like Frank Taylor before him, Wegener's theory was almost immediately dismissed by the geoscience community. He was, after all, just a weatherman. If Wegener and his continental drift theory were on trial, the prosecution would contend that all the evidence was circumstantial. He had no hard evidence to support his theory, and he couldn't account for what powered continental drift. The absolutely immense forces that must have been at work were a mystery. The story of how continental drift theory eventually became the modern theory of plate tectonics is fascinating and worthy of a video all of its own. I'd be happy to make it, so let me know in the comments if you're interested in seeing it. But it would make an already long video even longer, so here are the cliff notes. It took many geologists, geophysicists, and oceanographers years of work, often independently, to gather the patchwork of evidence that would eventually coalesce into the plate tectonic theory. One of the first breakthroughs came in the 1950s in the field of paleomagnetism, the study of the Earth's ancient magnetic field, a key part of which is studying magnetism in old rocks. Igneous rocks begin their lives as lava. When lava cools and hardens, iron oxides in the newly formed rock preserve the direction and intensity of the Earth's magnetic field. It is frozen in time within these new rocks. When scientists examined the magnetism of rocks from different parts of the world, they discovered that the direction of the North Pole was not stationary, but instead had apparently moved around quite dramatically. There were two possible explanations for this. Either the continents were stationary and the magnetic pole had moved over time, or the pole was stationary and it was the continents that had moved. As more rocks were examined, it soon became clear that although magnetic north does wander, there was too much variation in the magnetic data from the rocks to account for this polar wander. The continents were in motion. The next question was how? During World War II, Howard Hess was the captain of troop transport ship the USS Cape Johnson. The ship was equipped with a new piece of equipment called a fathometer, a depth sounder that was supposed to be used to help the ship navigate in shallow waters. But Hess, whose pre-war career was spent teaching geology at Princeton, was fascinated by the device and he never turned it off. Hess produced thousands of miles of echo-sounding surveys of the ocean floor. After the war, he returned to Princeton and continued to ponder the mysteries of the seafloor. In the 1950s, oceanographers discovered that there was a massive rift valley running down the length of the Atlantic Ocean. The Mid-Atlantic Ridge is the world's longest mountain range. It extends for about 10,000 miles or 16,000 kilometers in a curving path from the Arctic Ocean to near the southern tip of Africa. And down the middle of the mountain chain is a rift valley up to a dozen miles wide. When in 1960 core samples showed that the ocean floor was quite young at the Mid-Atlantic Ridge, but grew progressively older as you moved away from it, Harry Hess revisited his seafloor data and developed a new theory called seafloor spreading. Hess believed that at the bottom of the rift valley, magma from the mantle reaches the seafloor, erupting as lava and producing new crust, which was then pushed away from the central rift. The Atlantic seafloor was effectively two large conveyor belts, one carrying crust towards North America, the other carrying crust towards Europe. By 1968, all the strands were pulled together and most scientists agreed that the entire crust was moving, not just the continents. The name continental drift was discarded in favor of plate tectonics, named for the fact that the crust is split into 7 major plates that slide around the surface of the planet, powered by the immense heat and pressure deep inside the Earth. If you wanted to find the volcano that created Nebraska's Ashfall fossil beds, you might return to Idaho and the Bruno Jarbridge Eruptive Center, believing there was a volcanic hotspot beneath your feet. But you'd be wrong. The hotspot is still there and it hasn't moved, but Idaho has. Thanks to plate tectonics, we know that in the intervening 10 million years or so, the North American tectonic plate has moved, placing the hotspot directly under one of the United States' most popular destinations, Yellowstone National Park. In the 1960s, while studying the volcanic history of Yellowstone National Park, Bob Christensen of the United States Geological Survey became puzzled about something. He couldn't find the park's volcano. It had been known for a long time that Yellowstone was volcanic in nature. That's what accounted for all its geysers and hot springs. And one thing about volcanoes is that they are generally pretty conspicuous. But Christensen couldn't find the Yellowstone volcano anywhere. In particular, he couldn't find a structure known as a caldera. Most of us, when we think of volcanoes, think of the classic cone shapes of Mount Fuji or Kilimanjaro, which are created when erupting magma accumulates in a symmetrical mound. But there is a second, less celebrated type of volcano that doesn't involve mountain building. These are volcanoes that are so explosive they burst open the earth, leaving behind a vast crater or caldera. Yellowstone was obviously of the second type, and it was known to have erupted 3 times in the past 2 million years, resulting in 3 distinct calderas. But Bob Christensen couldn't find them anywhere. While he and his team were mapping the park, NASA was testing some remote sensing technology and advanced imaging from space. When Christensen combined NASA's satellite images with his own field mapping information, he realized why he had failed to spot the caldera. Virtually the whole park 2.2 million acres, was caldera. The most recent eruption, 640,000 years ago, left a crater roughly 45 miles or 70 kilometers across, much too large to perceive from anywhere at ground level. At some point in the past, Yellowstone must have blown up with a violence far beyond the scale of anything known to humans. In the 1970s, Bob Christensen began using seismic tomography, a technique that uses sound waves to image the Earth's interior to explore the ground beneath Yellowstone's caldera. He discovered a mantle plume, a volcanic area that, once you account for the movement of tectonic plates, was responsible for a number of truly cataclysmic eruptions, including the Nebraska Ashfall. Yellowstone, as it turns out, is a supervolcano. Under Yellowstone National Park, deep within the Earth's mantle, is a hotspot, a plume of magma rising through the mantle, melting rocks in the crust and creating huge magma chambers of partially molten, partially solid rock close to the surface. The heat from the hotspot is what powers all of Yellowstone's vents, geysers, and hot springs. The magma chamber below Yellowstone is roughly the same size as the caldera, about 45 miles across and about 8 miles thick at its thickest point. The pressure that this monstrous pool of magma exerts has lifted the entire Yellowstone Plateau about 500 meters or 1,700 feet above its surroundings. If it were to explosively erupt, the consequences would be unimaginable. And while Bob Christensen and his colleagues at the US Geological Survey were considering just what impact an eruption at Yellowstone might have, nature prepared a demonstration. In March of 1980, Mount St Helens in the northwestern United States began to rumble. A shallow 4.2 magnitude earthquake centered below the mountain's north flank signaled that the dormant volcano had just woken after years of hibernation. Volcanologists working for the US Geological Survey were called in to monitor and forecast the volcano's behavior. One of the first geologists to arrive on the mountain was David Johnson. Mount St Helens had been largely dormant. The last activity on the mountain was recorded in 1857, so Johnson and his team based their forecasts on the behavior of Hawaiian volcanoes. Mount St Helens, however, was a different proposition entirely. The mountain began spewing modest amounts of lava and ash on March 27th. Loggers, forest rangers, and residents of nearby Spirit Lake were evacuated as a precaution. But as the days turned into weeks without a major eruption, David Johnson and his team of geologists were under pressure to reopen the area. But they held firm, believing an eruption was imminent. On March 19th, the northern flank of the mountain began to bulge conspicuously. Unfortunately, no one on the team monitoring the mountain recognized that this bulge could indicate a lateral blast. The Hawaiian volcanoes on which they were basing their forecasts didn't blow out sideways. A lateral blast simply didn't fit their understanding of Mount St. Helens' past. A local geology professor called Jack Hyde, however, did recognize the danger. He pointed out that unlike Hawaiian volcanoes, Mount St. Helens didn't have an open vent, so the building pressure was bound to be released dramatically and probably catastrophically. Hyde was not part of the official team, and tragically, his observations attracted little notice. The US Geological Survey teams established observation posts called Coldwater 1 and 2 to study the impending eruption at what was considered a safe distance. When, during an interview with a local newspaper, Jack Hyde was told about the Coldwater posts, he said, "I hope they're not in a direct line. That's like looking down the barrel of a loaded gun." David Johnson took up a position at Coldwater 2. It was 10 kilometers or 6 miles due north of the mountain's bulging flank. At 8:32 a.m. on Sunday the 18th of May, a 5.1 magnitude earthquake shook the mountain and the entire north side of the volcano collapsed, sending an enormous avalanche of dirt and rock rushing down the mountain slope at 150 miles an hour. To this day, it is the largest landslide ever recorded. 1 minute later, the GOES 3 weather satellite captured these images. With its flank severely weakened, Mount St Helens exploded with the force of 500 Hiroshima-sized atomic bombs, shooting out a murderous hot cloud of ash, rock, and scorching gas at up to 650 miles an hour, much too fast for anyone to outrace. 10 kilometers away at Coldwater 2, David Johnson saw the blast and attempted to radio back to base, but the pyroclastic flows of ash and rock accelerated to near supersonic speed, covering the distance in less than a minute, and Johnson was overwhelmed. Many others who were thought to be in safe areas, often far out of sight of the volcano, were also overtaken. 57 people were killed in the blast. The body of David Johnson and 25 others were never found. Ash from the eruption began to rain down as far as 80 miles or 128 kilometers away. It turned day to night and got into everything, clogging motors, generators, and electrical equipment. It choked pedestrians, blocked filtration systems, closed roads and airports, and killed crops. Even today, more than 40 years after the eruption, debris is still present in Spirit Lake at the base of the mountain, and the surrounding hills are stripped bare and scarred. Having just seen the devastation caused by the eruption of Mount St Helens, you might be asking, what would an eruption at Yellowstone, the world's biggest active volcano, look like? It would be worse. A lot worse. The most recent Yellowstone eruption 640,000 years ago was at least 1,000 times greater than that of Mount St Helens. And the one 2.1 million years ago was so big that nobody is quite sure exactly how big, but it was at least 2,500 times greater than Mount St Helens. If an eruption the size of the one that created the Yellowstone caldera were to happen today, the effects would be catastrophic. Anyone caught within 80 kilometers or 50 miles of the eruption would die almost instantly. Within 200 kilometers or 125 miles, the heavy ashfall would collapse all buildings. People unable to evacuate would die along with all vegetation, livestock, and aquatic life. Power and telephone lines would break, and roads would become completely unusable. At a distance of 800 kilometers or 500 miles, the immediate threat of the ashfall is reduced, but it would destroy infrastructure and lead to substantial loss of life, all within the first few hours of an eruption. As the hours turned into days, most of the United States from coast to coast would see ashfall. Lung damage from breathing ash would be widespread in humans and animals. Crops and livestock would be affected by the contamination of food and water supplies. And the areas that would see the thickest ashfall are some of the most fertile farmland in the US. Food production would be devastated. And it's worth remembering that ash is not like a heavy snowfall that will melt in the spring. If you want to grow crops again, if you want to use roads or rail to transport those crops, you will have to find a place to put all that ash. It took thousands of workers 8 months to clear 1.8 billion tons of debris from just 16 acres of the World Trade Center site in New York. Imagine what it would take to clear an area spanning most of the United States. And the ash wouldn't stop at the border. Ash clouds would migrate across the globe, blanketing soil, contaminating water, halting all travel, and clogging machinery. Beyond the ash, the Yellowstone eruption would release enormous amounts of sulfur dioxide into the atmosphere, causing global temperatures to drop. This volcanic winter could last for several years. Crops and food supplies would suffer hugely, and prices would increase dramatically. Global famine would be inevitable. The last supervolcano eruption on Earth was in Toba in northern Sumatra 74,000 years ago. No one is quite sure how big it was, but it was a big one. Ice core studies show that the Toba blast was followed by at least 6 years of volcanic winter. It's believed that the Toba eruption may have carried humans right to the brink of extinction. That is a lot of bad news in a short space of time. So you might ask, how likely is it to happen? The US Geological Survey estimates the yearly odds of a Yellowstone super eruption at about 1 in 730,000. To put that into perspective, you're more likely to get struck by lightning than to witness a Yellowstone super eruption in your lifetime. However, if Mount St Helens taught us anything, it's that volcanoes do not work in predictable ways, and their eruptions do not follow predictable schedules. Despite advances in our understanding of the Earth, the world beneath our feet is largely still a mystery. Thanks for watching. If you haven't already, please hit the like button and consider subscribing to the channel.